Thank you. Well, I should start. I don't have a later slide, so I'll just start by thanking the Allen Institute to start. And not just for all the work, but really just for energizing the whole Northwest neuroscience community. And I think this symposium is a great example. And I may need, let's see, we'll get going when we get the videos. What I want to talk to you, I've had really a great opportunity over the past 10 years interfacing with the engineering community and Raj Rao and the whole group, what is now the Center for Sensory Motor Neural Engineering, and looking at a very unique opportunity we have to study motor cortex and sensory cortex function and the rest of the brain in patients who have electrodes implanted for the purpose of diagnosing their intractable seizures. So these electrodes are in place for about a week, and they're sitting there recording, and we now can have the technology and the computational ability to look at a wide range of signals that are there when they do sometimes simple, sometimes more complicated behaviors. So the reason we're there in the first place is because once you failed, if you have seizures, and that's about 1% of the population that has some form of epilepsy, and up to a third of those people can't be controlled with medication. So if they have a source of the seizures, then we know that surgery works, at least compared to ongoing medical management. And sometimes when we're trying to figure out where those seizures are coming from, we need to do this implantation. And so these are just photos to demonstrate what it looks like. They sit on the surface of the brain. We can document where they are. We're looking at a scale that's different from some of the other studies that you may be very familiar with. You can see an example of how much closer we are to the signal from scalp EEG, but we're not looking at the same thing as things like the Utah array or any of the penetrating electrodes, which are going to look at a small number of units. So we estimate somewhere around 500,000 neurons. That's an estimate. I don't know what combination of inhibitory, excitatory, or what they are, but something that's a synthesis of around that scale. Most of you know this, but we're looking at different time scales, and that's most of what we're going to do is in the time frequency space. So when you look at an EEG, and for about a century, people have been looking at scalp EEGs to diagnose disease and to some extent to figure out function. Most of what you see visually is at the very slow range, maybe up to 8, 12, 15 hertz of signal. But a lot of the interest is down at the very fast frequencies, which is with most natural systems has a lot lower power. It has been known for a long time that you can see some signals related to motor function from the surface. It's a pretty robust signal that you can even sometimes see in single trials, that when you move one hand, you get a decrease, so less power in the beta range, roughly around 15 hertz, on the opposite side. And that's mostly specific for movement of the opposite hand. It starts just before you actually make the movement and then rebounds back to, actually overshoots baseline when you stop your movement. So that's been known, and we can see that in our corticography signal as well. And for many years, this was observed. You could almost visually see where motor cortex was when you have these arrays because of this beta peak. And then you'd hit a pretty big cutoff from the 60 hertz noise that's all over the place in the hospital. And that was about it, because you're sampling about 100 channels, and you're going to do this for several days. And so your data accumulation really is enormous until maybe just the past decade that we've been able to handle that. And what we see is a really different story when you go out to these higher frequencies. And this is transgression. When we first saw this and went back and looked, you make your discovery and then go look at the literature. That sometimes happens, we have to confess. And it turned out that Hans Berger, when he looked at the EEG back in the late 1920s, described this phenomenon, but it kind of got lost in later years. But the fact was that we didn't see a specific frequency, but rather this very broad, in frequency space, very broad range of increase in power. And this increase was spatially pretty specific, because even though the beta change will lateralize to one side or the other, it's not spatially that specific, especially when you're on the surface of the brain. But we could see with really just within a few square centimeters, changes that were very specific to hand movement. And so this was our setup. We'd have the patient there at their bed. They're stuck at bed rest for the week. We split the signal to our research amplifier and have that connected to the laptop, which is connected to the graduate student, which does the experiments. So this is an example of how great this signal to noise is. I don't know if this will, sorry, I didn't ask ahead of time how I can run a video off this. Is that something I can run from here, or video? Anybody? No? Yeah. There we go. You got to click behind it. It's hidden behind it there. But okay, so going on behind that screen there is a, yeah, I don't have any control up here for the talk. Anyway, what you see is that you can generate a map in just 15 seconds. So with just 15 seconds of baseline, you'll see a map that's very specific to that area. That's what it looks like. That's pretty good. I predicted this, yeah. So that's your final map right there, which shows the area that's involved in just a handshake and single trials. So very powerful. And we can map out. We know a lot about motor cortex long before we do these studies. We know that this concept of the homunculus, where different parts of the brain, or of the body, map to different parts of motor cortex. And you can see that in motor cortex, and you can see that in sensory cortex. This is not unique to humans. The different parts of the brain have a representation that isn't obviously one-to-one with the body, so that's why whiskers are so interesting in rodents, because they have a ton of brain area dedicated to that. And you can see for the different animals, depending on what they do and what they specialize in, you see different amounts of brain representing that. This takes this example even further in kind of a grotesque way, which I like, which is the different moles. And try not to think about that tonight. So anyway, this is what we found, and it wasn't necessarily a surprise, but the ability to distinguish and to separate out hand and tongue areas using just this mapping method was really strong. And then what we looked is, well, can we do even better? Can we start to separate out even more discrimination across different tasks? And so, in fact, yes, when you look at the thumb and index finger, you can see different representations. So now we have a tool that's kind of interesting, because when you get and now talk to the engineers and say, well, what can we do now with what we currently know about the brain and what we currently can measure that might be new in the restoration and neuroprosthetic world? So, well, if you can separate out a thumb signal and an index finger signal, and maybe even know when neither is going, because actually that rest versus not moving may be the most important thing, and maybe even when they come together, well, now you start to have a range of activity. So in this next one, hopefully we can get this video to go. I don't know if somebody can click on that. Here we go, good. So now we're going to run through it twice. So we have the instruction. That's the patient's hand digitized there. They're going to move their thumb, and we're only going to look at 3 electrodes on the brain, put it through our classifiers, and send it to the robot. So when they're asked to move their finger, index finger, classifier gets index finger, and the robotic hand moves. These are all aligned in time, so you can see that just as quickly as the actual movement, we can get a robotic movement. We had one error there. And now at the pinch, so now we got both of them together. So we have rest. It's not moving when we don't want it to move. We get the digits, and we can get the pinch. And with this, we're up in the, you really need 100%, but we're in that 98, 97% accuracy. So that's not far away from an application of something that actually could be very useful. So what else can we look at? Well, we've been looking at, whenever you use something new or old, you have feedback. And we want to look at models of that feedback that can tell us how you might eventually interface with some kind of a device that uses these cortical signals to restore function. So the basic model, and we stole this from the EEG world, was have one channel and put that to a cursor that goes up and down to a target. It's very simple. You make the velocity of the cursor match the difference from the baseline of the power in this area. Picked an area that was pretty strong signal, pretty robustly went up. And then we just picked a motor area, partly because we were constrained by time, and partly because we understood what was going to make that go up or down. And so the initial instructions are usually to think about moving your hand, or move your hand or tongue, depending on our coverage. And then in doing that, make the cursor go up and down. And this relates to a bunch of things. This isn't going to work here, but we're not doing something as sophisticated as what you've seen with, say, the group that have been working on BrainGate, so out of Brown and Harvard, or the Pittsburgh group that's had microarrays, and these have been in patients with motor disorders, very fancy. What we have is really sort of a Pong game version of that. Much, much simpler, but we can do it in this short period of time. We can do it in people who are coming through. We do about 30 of these operations a year. At least half of people are interested in participating in these and able to. And we can study what, at least in this relatively short window, people do with that. And the first thing you see, is that when they move, if you ask them to imagine doing a movement instead of actually doing the movement, you still get a pretty strong signal. It's about half of the signal that you get with the overt movement. And that's impressive because you lose all of that proprioceptive feedback. You don't really know what they're doing when someone imagines moving, but there's still a pretty strong signal in these same areas. But then when you give them this feedback and say, okay, take even this imagined movement and drive a cursor one direction or another, you actually can get a power in that area that exceeds what you got with an overt movement. So you can volitionally ramp up this signal to be even beyond what you get with movement, while all you're doing is thinking about moving the cursor up or down. And the other thing you do is you get better at that task. So if I just give you a 50-50 task, most people start out at about 50-50 when they first get this because there's nothing intuitive about it. But really in the matter of about half an hour, you can get pretty strong learning. This is you can get 2 different channels and try to get more targets, but even the one channel, you see that over a period of time, you get a pretty robust increase in performance. And so we can look at a variety at these changes that occur with behavior at a variety of different levels. We're not looking at the neuron level. We can behaviorally see it, but we also have the opportunity to see what's going on in cortex during this because the electrodes are recording from more than just this one area. And so what we see, if we could play this video from somewhere, there we go. And you're going to see when you first start out, so now I've just set the horizontal velocity fixed, and all they have to do is move the cursor up towards the target. And this is one channel. And you see the first day, first starting it, getting down may not be that hard, getting up pretty hard. Now after a couple of days of practice, this is obviously different. And so these are 2 different brain states now, the novel state and the learned state. We haven't changed anything else. We haven't changed the weighting. We haven't changed the task. It's all been figuring it out and doing it differently. So what does that look like behaviorally? Well, the first thing you do is since the rest is kind of leaving things alone, and the red here is the up, which is more power in that area, is you crank the power up. So like I showed you, you can increase that power even beyond what you get with movement. And then but then you actually don't, then you stop doing that. And then you get increased accuracy, not by more and more power, but by consistency. And so you see that the red dots no longer as high as they were in run 2 when you get to run 3, but they're more consistently above that green line. And then by run 4, they're all above that green line, and all the blue are below that green line. So your accuracy is 100%, but the black line, which is the difference between the red and the blue, is actually lower in run 4 than in run 2. And it turns out that that's how you learn most motor tasks when they're novel. But what else is going on here? And one of I like these slides for a couple reasons. One is sort of well, it's just kind of fun. But the 2 brains below are 100,000 years apart in evolution. And so you see that there's massive increase in growth. And I'm not going to explain why that happens. I have no idea. But but the other cool thing is you look at that. That's a log-log plot of body mass and brain mass. And most mammals are on that line with the dark circles, but human evolution just takes the straight vertical deviation from there. And with the exception of maybe dolphins, there's really nobody else that has this large a brain for body size. And then the birds and reptiles are on the open circles except for the crow, which has actually, even if it were a mammal, would have a big brain. So keep that in mind. But the other important thing is that when I say I'm recording from motor cortex, I'm actually probably not talking about the same thing as when Beth Buffalo or others are recording from motor cortex, because that homolog, as best we can tell, is actually buried within the sulci. So when I'm talking about what we would clinically call M1, we may be looking more like area 6, which is premotor. So there's a lot of reasons to think that what we're looking at may behave a little bit differently from what we understand about motor cortex. But then it also means that we're recording from a lot of things where we really don't have a lot of experience in the primates, at least that I'm aware of, in terms of what these parts of the brain might be doing. Because as I'm going to show you, we have a lot of sampling from much more anterior in premotor cortex and frontal lobe. And so what might some of these areas be doing? We had a lot of extra brain there, and we can record from it. Well, of course, there's many, many things that could be going on. One of the things we see from functional MRI work in healthy volunteers is that especially when you do something new, examples here, you get a very large activation when you're starting to do a task that goes away when you're doing the task in a more learned state. So in this case, frontal lobe activity on both sides when you're doing a new verbal learning task, and also some involvement in the medial frontal cortex. So we can look at that in our patients. So this is one example of somebody, and that's the brain doing that cursor task up and down. So this is the up portion of it over time. So for the 4 different trials or the 4 different brains up there. And now if we say both the absolute and the ratio of what changes between the beginning and the end. So the control electrode is down there in motor cortex, face motor. So it's weakly yellow because that did increase in its activity. As I showed you, it doesn't go way up, it goes somewhat up. But then look at at the blue, which are the negatives. And so there's this whole area in frontal lobe that's less active once you've learned it than before. And so you can see that in individual trials. So this is an example of a piece of brain just in front of motor cortex. And its activity is pretty high while you're moving the cursor up or moving it up, a little bit high when you're moving it down. And then something happens. That black line there is actually derived from the behavioral data. So if you see where does the distribution of the behavioral data change, that's exactly the point where you see this transition from a very frontal lobe active state to one where the frontal lobes really aren't doing a whole lot while you're doing the task. And we don't have a tight link to it, but a lot of times what people will say subjectively is, oh, well, I went from thinking about moving my hand to make the cursor move to thinking I just wanted the cursor to move. And so somewhere in there, you've made it to some degree automatic. And this is what it looks like across all the subjects. So if we put everybody together that had done this, and we see that there are these consistent areas in frontal lobe and parietal lobe that are more active when you're starting to do the task than when you've learned it. And interestingly, if you go back through the functional MRI literature, you see that these exact same areas are popping up. So we're taking a task that they never could have possibly done before. We're harnessing a piece of cortex directly to do the task, and you have this system already in place to let you learn it. So that has some pretty big implications for any kind of future neuroprosthetic use. It means that you may not have to figure it out exactly because your ability to learn it may very well be intact. But that's the overall goal of what the center is trying to do, is to get these signals delivered out to a controller, eventually get our controller into either a robotic space or maybe restoration of existing limbs, and also to get information back with the sensory component. I'm going to skip through a couple examples here of what we can do and ask this question, because once we've figured out what we can map to, we're making an assumption that the homunculus may not change a whole lot. So is it really static? We know it's not. If you have an arm amputation, the map changes. The areas that are adjacent to what you lost will fill in those spaces. And so you get a reorganized homunculus that doesn't leave anything blank but fills in. So we wanted to see what happens when we harness this area of the brain to do something different. And we had a task that was consistent, that would always give us activity. So this force bulb task, it would activate motor cortex. And then we would use the strongest piece of that activation to drive this BCI. Do that for about 5-10 minutes, and then repeat the task. So what you get when you started is strong motor sensory activation. Again, use the strongest area to drive the BCI task, and then see what happens to this distribution. And here's what happened, is that same area actually winds up decreasing its activity when you do the exact same motor task before and after. So what you see is that you've taken this piece of the brain, done something else with it, and then when you come back and do what it was originally tuned to, it cares much less. And so what you've really done is in some way reassign this area and in some way modify the homunculus, at least transiently, to repurpose this area. But the person can still do this task fine, so what's going on? So we changed it a little bit with the collaboration with the group of Karsten Mehring in Freiburg, And this also built on work that Dev Sarma and Raj Rao had done with EEG and also with corticography. And we said, okay, you're going to make the cursor move left or right by using a keyboard, key press. And now we're going to take the piece of the brain that's most active when you do that, and that's going to be your other dimension. So you can move the cursor up and down with your brain, but that same piece of brain should be involved in moving the cursor left and right because you're using your hand to do that. So if there's no ability to separate those out, you'll never be able to go in the diagonal because by moving the key press, you'll drive it up. And you certainly couldn't go in the lower diagonals because by moving the key press, you'll get power in that area that should drive the cursor up. But when you look at it, you actually had no problem moving things in the lower diagonal. So that means you were able to move the key press, but you turned off that piece of the brain that was maximized for that part. And so this is what it looks like, is that when you are moving the cursor up, it has to be red up there because that's what makes the cursor go up. And when you're moving the key press, pressing the keys, your motor cortex is active. That's the red on the left and the far right. But somehow you're able to turn that off and keep that blue in the lower two sections. And so that just shows you that we aren't repurposing that piece of the homunculus. We're actually expanding it and allowing it to exploit some kind of transient plasticity that exists there. I don't have time to talk about this other one, but we can give sensory information back to cortex. And we do this for clinical purposes all the time. People can get a sensory percept from it. And you can see in multisensory integration areas activity that goes out throughout that when you have the visual stimulus that matches this sensory perception. You can create the illusion of touch with cortical stimulation, and we can actually match that to what they call the rubber hand illusion, where you have a model hand that is not your hand's hidden, and you can actually get the perception that your hand is being touched, and that's what we're showing here, is this subjective perception that you can create through direct cortical stimulation. I just want to quickly wrap up with what this can look like. This is a real-world application. Andrew Coe, Howard Chiswick, Jeff Herron, Maggie Thompson in the electrical engineering lab have been working with, from a gift from a Medtronic this is a closed-loop system, and we actually have now 2 patients that have implants. This is the kind of signal that we can get, and these are deep brain stimulators placed for essential tremor for clinical purposes, but they have an additional 4 channels of corticography where we can see these kind of intent-related and movement-related signals that we can, if we can get these signals to then drive the stimulation, we have the possibility of actually having a closed-loop system this year. So that's how close we are. This is the enormous amount of collaboration and work that goes into it, thanks to the Allen Institute and the multiple funding agencies. Thank you.
Dr. Ojemann, for such a great talk. It does make you wonder what's real and what's not real these days. If you have questions, we'll have some mics. There's a mic coming to you from over there. And oh, okay, and there's another one here. So first,
I was wondering
okay,
if
one
you
and then
could please talk about more about how you were, what methods you used to teach the computer to understand the data that you were looking at.
Nothing. That messes it up. So I'm talking about with the closed loop.
Yes.
Yeah. You just say above this power is up and below this power is down. When you try to do the learning ones, the first time we did it, the person had well below chance performance because by the time the user figured it out, the computer was making changes. And so either we have to get much, much better with those algorithms or train people differently, or both. So it wound up being, for the first several years, counterproductive. It may ultimately be very useful, but that's where we stand.
So you were saying that the patients describe the training task as suddenly becoming automatic. I wonder if you've ever tried this or what you think would happen if you haven't. If you could just visually switch flip the vertical axis on the display, such that now they are using they're using the electrode power to move to move it down, and whether you think you would have to completely re-entrain or just from that visual.
Right. So that's exactly what we need to do. We haven't, because you have 2 parts of learning, right? There's the mapping, but there's always what in the world am I supposed to be doing? So there's the task-based piece of it and then the state-based piece of it. And that's, it should be some intermediate thing where you'll do awful, but you'll relearn it pretty quickly because you just have to remap the rules. Yeah, we thought of that, but you could do something even more gradual, or mess with make it where it's no longer just a linear relationship to the power and all those sort of things. But yeah, not yet. Great.
Yeah, we have another question right
The
there.
homunculus is so the homunculus is able to expand to handle additional tasks. As I recognize that I'm talking well beyond the scope of our current capabilities, but if a virtual reality system was convincing enough, could the brain adapt and expand the homunculus for possibly additional limbs in virtual reality?
Yeah. So yeah, people have done that. The Marion group is, not with this invasive technology, but they've looked with functional MRI at trying to give people a third-hand illusion. You can do that with mirrors, and they study the psychophysics of it. So yeah, you can modify these body maps, these kind of things, at least pretty quickly, at least on this particular task. For this particular task. In other words, I'm not sure that those people walk out and think, oh wait, where's my missing third hand? But certainly for the short term. And so I don't know exactly what's going on. I'm not sure that you're really, how much is modifying the homunculus and how much is saying, okay, just like when you learn a new task or do a maze or something, you're modifying how you use your pre-existing system.
And which group did you say it was that was working on that?
The third limb?
Yeah.
This was at University of Freiburg, Mehring, M-E-H-R-I-N-G.
Thank you.
Oh, question up here.
Can you say anything about how a performance metric of, putative prosthetic control might compare with an ECOG-based detection as opposed to the unit-based systems like they're doing at Stanford and Brown and stuff?
Yeah, well, no, units are fantastic. So you have always a spectrum of invasiveness. There's really no reason to be invasive if you aren't doing better. The challenge it's funny because some of the unit world is now looking more at fields and looking at, because if you have the unit information, and Richard Anderson has got some really nice examples of this, you have an enormous amount of information about the different states, the different tasks. But you don't necessarily have as much information about the different brain states. And so, something as simple as alertness versus sleep, those kind of things might be best at a more integrated level. Much of what we're looking at, if you go and look at the individual neurons, at least in the primate, they aren't as homuncularly organized. So you will have a first digit and a second digit neuron not very far from each other. So if you want to know what you're going to get ahead of time, the unit approach has some challenges. But the biggest difference right now is the longevity. These can encapsulate, and you're still going to have a pretty decent signal. I would be extremely reluctant to say you can only use X signal or Y signal for the future application. It seems like you throw everything at it.
One more question up here.
So you said you can use non-motor areas to do a motor BCI task. In some cases, I thought you said that you could.
I shouldn't have if I did, but
okay.
Yeah.
But is it possible then to, based on connectivity with, I don't know, let's say the visual cortex, if it does, it has projections to motor cortex, could you train?
Yeah, well, so two things. One is actually you can do it. The Dutch group, and we've done one or two examples where you can use, say, a working memory area or a language area to drive a cursor. So I guess that is a motor BCI. It's sort of been done. You can use, we've used connectivity between frontal areas and motor areas to do that, where you can volitionally control the strength between the two areas. I think where I would go with that is, okay, what if the motor area is damaged? What do you have left behind that you can do? I don't know. We've had a few really rare opportunities where somebody did have a small stroke, and we were in there putting these in, and what we found is you could usually see signals related to residual activity, and then a lot of ipsilateral signals. So from the healthy limb, you'll see a fair amount of signals still in that area. But I don't know if those connectivity or network signals, how healthy they're going to be. And they're certainly harder to get at than the direct local signal. That's about all I know.
Okay. Can I ask
Thank
one
you.
simple
Yeah,
question?
yeah.
I'm just going to ask one simple question, since we have about, I don't know, half an hour. So I was just wondering, you're saying that there's an increase in activity, then that after the person learns it, there's a decrease in activity. Is there a relationship between the extent of the increase and either the speed with which that decrease shows up?
Not in our data. In some other places where people have found this phenomenon, it's almost inverse. In other words, the people who are the slower learners, it's almost as if it's working harder.
Oh,
And you'll see that after, you can see it with drug effects and after in TBI, that this kind of global activity is, it's not clear that it's maladaptive, but it may be that if you're not that good at it, you need to work harder.
Okay.
It may be a secondary finding of that.
Okay. Thank you very much.
Okay, thanks.
Again, thanks, Dr. Ojemann.